In Chapter 6, Section 3, we're going to start focusing on two different vocabulary words. Remember, earlier we did in 6.1 and 6.2 perpendicular and angle bisectors, and now in 6.3 we're going to focus on median and altitudes of triangles. So, again, vocabulary is very important. Memorization is very important. The median of a triangle, okay, is a segment from a vertex to the midpoint of the opposite side. So if I look at this triangle here, triangle ACB, I notice that if I'm at, let's say I'm at vertex C, I'm up there at the top. If I'm at vertex C, the median is going to go from the vertex to the midpoint of segment AB. And basically, it's going to go down. And notice that what that median does is it splits the segment in half, right? And I can do, for example, multiple medians. So like that's the median from C to D. But I can also do a median, for example, from vertex A. I can figure out where the midpoint is here, I'm guessing right now, of BC. And so this would be the median of vertex A, right? And then I could do the same thing with vertex B. Okay, I would, need to know where the midpoint is, right? And I would draw this one, okay? And so when I do that, I know that this segment's going to equal this one. When I did the blue median, I knew that this segment would equal this one. And so what the medians do is they split the opposite side into equal parts. And you're going to see that when we do that also, our medians are going to have a point of concurrency as well. Just like what we learned with the other ones. And in a subsequent slide, we're going to learn what do we call that point of concurrency and what can we do with it, okay? But basically, every triangle obviously has 3 medians. Okay, that's what I just showed you. There's 3 of them because you draw one from each vertices. Remember that the vertices is the vertexes. It's the plural name for the vertexes of a triangle. And again, they're also going to be concurrent. That's what I just showed you, that they're going to have a point of concurrency. They're going to intersect in a point. Now we're going to go to the word centroid, okay? Again, another vocabulary word. This is the point of concurrency of the medians is called the centroid of the triangle. So back in that other slide, that point that I found, that point of concurrency was called the centroid. And again, the centroid, much like the incenter, is always inside the triangle, okay? Now the centroid is also called another name. It's called the center of gravity. And it's called that because it's the point where a triangle region will balance, okay? If I was to, look at the picture, you're sort of, it looks like a nail, and they're laying the triangle flat on that nail. Well, this point right here, okay, where those medians are meeting, that's called your centroid. And if I balance that on the nail, my triangle should balance. It won't tip over in any direction. That's just kind of just a fun fact. So, and again, as everything else, now that we know how to identify the centroid, now we're going to apply it with a theorem, okay? And the centroid theorem basically tells us that the centroid of a triangle, that point of concurrency, is 2/3 of the distance from each vertex to the midpoint of the opposite side. It's 2/3 of the distance. So that's kind of interesting. Now let me look here and show you what we're talking about. Again, notice those blue lines are your medians, okay? Notice you're going, for example, from vertex A to the center or the midpoint of BC. Then you're going from vertex B to the center or midpoint of AC, and you're going from C to the center or midpoint of AB. And so when I connect all those medians together, I get this point of concurrency, which we know because it came from medians, it's called the centroid. Now what's interesting is that if I take these segments that I created, these medians. If I take this entire median, BF, I know that 2/3 of the entire segment is going to be represented by this top piece. 2/3 of the whole thing is going to be the top piece, and 1/3 of the whole side is going to be, of the whole segment is going to be the bottom piece. So there's going to be a longer section and a shorter section, and you just need to know that the longer section is 2/3 of the total, and the bottom section is 1/3 of the total. So again, imagine if you knew that AE was equal to 9, okay? Then I know that AP here, this longer section, is 2/3 of 9. And when I actually do the math, I see that that's 6. And so that's, if AE is 9, AP is going to equal that. And PE is going to be 1/3 of 9, or 3. And again, together, notice they add up to the full 9 units of the segment. But again, really interesting. That formula is interesting. Now let's do some problems with it. It says in triangle LMN, S is the centroid. So point S is our centroid. We know that. Okay? And again, notice you have a longer half and a shorter half of various things. Firstly, they tell us that RL, this yellow segment right here, they say that RL equals 21. Well, what I know is that from L to S, okay, LS is going to be 2/3 of RL, which is 2/3 of 21, which is going to be 14. So LS, this segment right here, is 14 units long. And just so we can, so you can see it, I know that RS is going to be 1/3 of 21, or 7. Okay? And then again, I go to the next question. They tell me that SQ equals 4. Okay? Well, again, now they're giving me the bottom piece, right? Well, I know that SQ is going to equal 1/3 of the entire segment NQ. Okay? So I can kind of work this out a little bit backwards. If I know SQ is 4, then I know it's 1/3 of NQ, whatever NQ is, right? Well, I'm going to solve for NQ. I'm going to multiply both sides by 3. That's going to cancel that, and it's going to be 12 equals 1 times NQ, or 12 equals NQ. And that's it. So NQ equals 12 units long. I know 1/3 of it is 4, and 2/3 of it is 8. And so I know that that's the answer there. So again, you got to be careful. There's lots of things I can ask you for. I can ask you for the segment that's 2/3 long. I can ask you for the segment that's 1/3, or I could ask you for the entire segment length. So there's a lot that can be asked in these types of questions. Let me give you another example. In example 2, it says a sculptor is shaping a triangular piece of iron that will balance on the point of a cone. Again, if they're talking about that it's going to balance on the point of a cone, I know that for balance, I'm looking for the centroid. Okay? Absolutely 100% looking for the centroid. So when it says at what coordinates will the triangular region balance, they're saying at what coordinates is the centroid located. And again, remember that you're drawing a line to find that point of concurrency and that centroid. You have to draw a median. So you have to go to each vertex, and you have to draw a line from that vertex to the midpoint of the segment. So I'm going to have to do a little bit of math here, because I'm going to need to know, for example, I'm going to start with this line right here. I'm going to need the midpoint of 6, 6 and 10, 7. Well, what's the midpoint of that? Remember that the midpoint is the average of my x's and the average of my y's. So the midpoint is going to be at 16/2 and 13/2, which is going to be 8, and it's going to be 6.5. So at the coordinate 8 and 6.5, 1, 2, 3, 4, 5, 6.5. Right here, that's the midpoint of that section. So now I'm going to draw my median from this center to that point, okay? Now, I'm going to do the same thing with the other side of my equation. So I'm going to come over to here. Let me do a different color. I'm going to do from 10.7 in purple here over to 8.2. And I'm going to find the midpoint, again, from the ordered pair 10.7 and 8.2 from that purple segment. So again, I know the midpoint is the average of my x's and the average of my y's. And it's whatever that ordered pair ends up being. So 18 over 2 is 9, and 9 over 2 is 4.5. So I know the midpoint of this purple segment is at 9 and 4.5. So 9 is here, and 1, 2, 3, 4.5. Right there is the midpoint. And so I'm going to go from here to there. And then the last one I'm going to do, and I'll make it this blue line here. That one, I don't want to do blue. Hold on. Let's just stick it. Let's keep it with red. So it's going to be this red line here that's left over. And again, I need to find out the midpoint of the red line. It's, again, my coordinates are 6, 6 for one endpoint and 8, 2 for the other. And I know that my midpoint is going to be, oh, I already wrote midpoint, sorry. So my midpoint is going to be the average of my x's and the average of my y's. So it's going to be 14 over 2 and 8 over 2, which is 7 and 4. So the midpoint of that segment is going to be 7, 4. 7 is here, 1, 2, 3, 4. There's my midpoint right there, and I'm going to draw it from there. So now that I drew my 3 medians, notice my 3 different colors from my 3 sides to my vertices, I notice that I have a point of concurrency right here. That is my centroid, and that is my point of balance, and that is located at the ordered pair of 8, and then 1, 2, 3, 4, 5. And so that is where I would need to balance that triangle on that piece of whatever, on the cone or whatever. So again, that's what we're doing. So that is my centroid. That is the ordered pair that they wanted. Now that we've done medians and centroids, we're going to get to altitudes. And again, altitude is a different thing. Again, we're going to vocab here. The altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. So it's a perpendicular segment. Notice it's not a perpendicular bisector. It doesn't split the other side in half. It just is a perpendicular line from the vertex to the line on the opposite side. Every triangle has 3 altitudes. Notice every triangle had 3 perpendicular bisectors. Every triangle had 3 angle bisectors. Every triangle had 3 medians, and every triangle has 3 altitudes. And again, you can find a point of concurrency for all 3 of those perpendicular segments, okay? All those altitudes, rather. And it can be inside, outside, or on the triangle. So again, this is very similar to the circumcenter from the first day, where that also could be inside, outside, or on, okay? So if we look at the first triangle here, we have, for example, our altitude from point Q. We're going to have our altitude, from point Q, 90-degree intersection with PR. It's perpendicular to segment PR. And so that represents the altitude. And notice that the altitude is inside of the triangle. Okay? If I go in this obtuse triangle here, if I go from vertices C, if I want to do a perpendicular line down, Well, what I have to do is I have to extend line PR. I have to kind of extend it out this way, and I have to draw my line down to it, okay? So the segment, this altitude, isn't even inside the triangle, but again, I have to kind of draw it outside the triangle because it has to hit at 90 degrees. No line that I draw from inside this triangle is going to hit PR at 90 degrees. So if the triangle's obtuse, my altitude is going to be on the outside. So again, what are we going to do with that? Well, we're going to describe what the orthocenter is because it comes from altitudes. And it basically says the orthocenter is the point of concurrency, okay, when of your altitudes, basically. The lines containing the altitudes of a triangle are concurrent. The point of concurrency is the orthocenter of the triangle. So again, the orthocenter comes from the altitudes, okay? So again, if I look here at this particular shape that they gave me, they show me where they draw an altitude from A to side BC, from C to side AB, and from B to side AC. Notice those three altitudes are perpendicular, and they meet at this point over here. This point right here is called the orthocenter. So again, the orthocenter comes from the point of concurrency made by altitudes. So again, it wants me to find the orthocenter of some triangle. So I have to start by drawing the triangle. Point X is at -3, -4. Point Y is at -3, +4. And point Z is at 5, 4. So I draw my triangle here. It's a right triangle, which is kind of nice. And it's time for me to find my orthocenter. Now, again, this is a little bit tricky because drawing perpendicular lines is not always easy. Remember that, if I'm trying to draw a line perpendicular to a diagonal line, I'm going to need to use the slope of the line and the opposite reciprocal and all that fun stuff. Thankfully, when I have a triangle like this, it's easy to draw perpendicular lines from vertices when the lines are horizontal or vertical. Notice if I'm at point Z and I want to do a perpendicular line to YX, well, guess what? This leg is a perpendicular line. So in a right triangle, my two legs are two of my altitudes. So there's one altitude. If I go to point X and I want to draw a line to the opposite side, I know that XY is my other altitude. So the last altitude that I need to draw, right, is going to be from point Y, right, at some point down to that line, right? So obviously, remember that the orthocenter is the point of concurrency of your three lines. Well, the point of concurrency is right here, okay? So my orthocenter is located here. I already know that because my other two sides intersected there. So I'm sort of done with this problem. Obviously, the coordinate plane or the coordinates of it is going to be -3, 4. That happens to be my point of concurrency, and that happens to be my orthocenter. Now, if I did have to just draw a perpendicular line to side XZ, again, I want to make sure that you can do it. So let's just draw that line, for practice, okay? I know that XZ, I can figure out the slope of that. Here's point X and here's point Z. The slope of that line, I can count if I want, or I can do the math. It's -4, -4, and then it's -3, -5. Remember, it's the difference of my Y's over the difference of my X's. So -8 over -8 or +1. So the slope of XZ is +1. So what that means is the slope of the perpendicular bisector is going to be the opposite reciprocal of 1, which in this case is just -1. So if I go over here to this point of concurrency, I already know that's it, then I'm going to do -1. So I know my line is going to go, like, let me erase that little arrow there. Okay, so I know it's going to go 1, 1, 1, 1, like that, and it's going to look something like that. And so that would be the third line. So my 3 altitudes are like that. They meet over here at Y, and that's my orthocenter. So the location of the orthocenter, again, is something you want to talk about. We already talked about the orthocenter being either in, on, or outside of the triangle. And again, it's kind of similar to the circumcenter. If the triangle is acute, your orthocenter is inside, okay? If the triangle is a right triangle, like we just observed, the orthocenter is on the triangle. Notice again, from this vertices to here, this vertices to here, or this vertices to down here, and this one to here. Notice that they all meet up at point P. And then again, in an obtuse triangle, notice the obtuse triangle is the black, okay? And when I draw those perpendicular lines, I see that it's going to be outside, okay? My orthocenter is outside, okay? And so, again, just things to kind of learn. So orthocenter and circumcenter have this in common, okay? So now to summarize everything we sort of learned, again, these are the 4 types of points of concurrency that you're going to have to memorize: circumcenter, incenter, centroid, and orthocenter. Okay, again, they're points of concurrency. The circumcenter is made by perpendicular bisectors. The incenter is created by angle bisectors. The centroid is created by medians. And the orthocenter is created by altitudes. Once we know what something is, like how it was created and what its name is, then we potentially have some additional information on it, right? The circumcenter theorem told us that the circumcenter was equidistant from the vertices of the triangle. The incenter, we learned that it was equidistant from the sides of the triangle. We learned that the centroid is 2/3 of the distance from each vertex to the midpoint, right, of the opposite side. I call it the longer side and the shorter side, but again, it's 2/3. So if you're at the centroid, okay, and this is the vertex, this is the 2/3, side, okay? I call it the longer one and the shorter one, but again, if you want to know, it's the one between the vertex and the centroid. The vertex and the centroid, the vertex and the centroid. Those are the 3 pieces that are 2/3 of the total, okay? And then this last one doesn't really have a formula. If you know you have the orthocenter, it just says that the lines containing the altitudes are concurrent at the orthocenter. So again, it's just telling you that these lines all meet here, okay? And that's it. So that one to me is not as useful for us. You're not going to get a lot of problems that have any, type of mathematical questions with that last one. I highly recommend you guys memorize this, and I highly recommend that you practice a lot of these. Look at Kahoots, look at different games online, just to kind of refresh your memory and practice visualizing these and applying the skills. We're going to do a lot of this in class as well.